Hi again. This is going to be module number 22. We looked at dynamic programming, and now we're continuing to linear programming. In linear programming, there's a formulation of a problem that is linear, and we're going to be optimizing this linear formulation. And this is useful because many real-world problems, they may not be exactly linear in terms of their utility, but they might be well approximated by linear. So our formulation involves a canonical form. We're maximizing C transpose times X. So C transpose is an input. We're interested in the best X. That's what we, double underlining, that's what we want, the X. And we want to maximize C transpose X, or find the X that maximizes C transpose X, subject to, first of all, every element of X is greater than or equal to 0. So this notation means element-wise greater than or equal to 0, every single element. And additionally, AX, where A is a matrix, is less than or equal to some vector B. Now, how can we interpret these? The combination of X being greater than or equal to 0 means that if we plot the X's, so this would be x1, and this axis would be x2, and this axis would be x3. And them being greater than or equal to 0 would mean that if you have 2 dimensions, one of the quadrants is where we are. And if we have 3 dimensions, it's called orthant. Orthant for 1/8 of the space. So we're in, and I'll switch a color, we're within this space over here. Think that it's kind of in front of us, toward us. And additionally, we want the matrix A times X being less than or equal to B. So let's think about that. It's, if AX is equal to B, that would be a hyperplane. So this hyperplane, we're sketching it like so, and maybe it intersects the edges of this orthant on these lines. So what I'm saying is that we have now the area of interest on the one hand is in that orthant, and on the other hand, it's behind the hyperplane, meaning that it's in this pyramid, okay? So we're finding the X that maximizes C transpose X, subject to X element-wise is greater than or equal to 0, and A times X element-wise is less than or equal to B. So you'll note that our inputs are matrix A, vector B, and vector C. The output is X. Now, this may seem like a somewhat narrow problem. Why would the X's be greater than or equal to 0? Why would AX be less than or equal to B? Maybe some of the values of AX are less than or equal to some B, and others are greater than or equal to. So maybe we have more complicated constraints. The real issue here is that there are various tricks that can be used, matrix manipulations, to create a lot of variations. So as an example, imagine that you don't want AX to be less than or equal to B, but you want AX to be equal to B. So suppose that we want to do that. So what we'll do, we'll be maximizing C transpose times X. ST is subject to AX is less than or equal to B, same format as before, minus AX is less than or equal to minus B. So I'm going to write in parentheses, this is equivalent to AX being greater than or equal to B. And by requiring AX to be both less than or equal to B and greater than or equal to B, these two constraints together mean that AX is equal to B. And we also want X greater than or equal to 0. Now let's rewrite that AX is less than or equal to B and negative AX is less than or equal to negative B. So let's say that A tilde is a concatenation of A and negative A, and B tilde is a concatenation of B and negative B. And now this joint constraint with two constraints is equivalent to the following. A tilde times X is less than or equal to B tilde. So we now have a variation that gives us a subject to equality instead of this inequality, and we achieve that by using this A tilde and B tilde construction. Now, what we've already discussed on at least one occasion that I remember, L1 minimization. And we're going to talk about L1 minimization when it comes to the sparse signal processing material and also machine learning. And now let's think about, just like we described how to enforce an equal to for the AX equals to B by modifying the canonical form of the linear program, let's now talk about how to enforce an L1 norm. So suppose that X is equal to XP plus XN. XP is a vector, XN is a vector, X is a vector, and XP is greater than or equal to 0. XN is greater than or equal to 0. Or rather, XP minus XN. We're subtracting the negative from the positive. And now the L1 norm of X1 is because XP is greater than or equal to 0 and XN is greater than or equal to 0, the L1 norm of each element I is either the absolute value of XPI or the absolute value of XNI. And if one of them is positive and the other one is 0, and because of that, Xi in absolute value is XPI in absolute value plus XNI in absolute value. As a consequence of that, X L1 norm is the L1 norm of XP plus the L1 norm, excuse me, of XN. So bottom line, we can do equalities, we can do L1s, we can do various things. And all of these can be expressed through this canonical form, where here X tilde will be XP and XN, and we'll be maximizing the L1 norm of X1 will, as I wrote earlier, it'll be the sum of the L1 norms of XP and XN. And basically, we can use the C tilde is an all-ones vector. An all-ones vector will be summing up over the values in XP and the values in XN, and we minimizing X1, or in the canonical form, maximizing C transpose X, maximum minimum up to a minus sign, they're the same. All these things can be handled through the canonical form. Okay, so linear programming, we have a canonical form, but actually covers much more. That's one of the messages that I'm trying to convey. Another message that I'd like to convey is, why is this useful? What's it good for? So imagine a transportation problem, and an airline is going to pose its costs and revenue using a linear model. Now, as we know, things are rarely exactly linear in the real world, but often things are approximately linear. So now the airline is going to be maximizing the profit, which means revenue minus cost, using a linear program. And if the linear model isn't exact, but if it's reasonable, the answer will be reasonable, because solving a nonlinear problem is probably very difficult. A second problem involves manufacturing. We're going to minimize costs and or maximize revenues by posing them in a linear form. The common theme here is that many real-world problems are approximately linear, and the Taylor series approach tells us that in many engineering applications, we linearize things around a working point, and if there are constants, offsets, to that working point, that's fine, but around the working point of interest, we're linear. Some history about linear programming. An early formulation dated back to the early part of the 20th century. There were rudimentary forms of very simple linear programming with a small number of variables even earlier. Dantzig, this gentleman that we see on the right, invented the simplex method, which is a type of solver in the 1940s. And the simplex method has a polynomial time average runtime. However, the worst case runtime is exponential in the size of the problem. And a more modern approach is called interior point methods. They have a much faster worst case than the simplex method by Dantzig, but on the other hand, the average runtime is comparable. So to give you just a bit of insight about the simplex algorithm, we have these linear constraints that ax is less than or equal to b, and x is element-wise greater than or equal to 0. This corresponds to a convex polytope. Polytope is a fancy mathematical word of saying basically a diamond, as you're seeing in this illustration. And the linear function, which is being optimized, is C transpose times x. And it can be shown that this linear function is optimal on a corner point of the polytope. And the simplex is the outer shell of the convex polytope. So what we're doing, we can start with this diamond, the polytope, and we find some starting vertex, and we start moving around the edges of the diamond, and we know that one of the corners is going to be optimal, so we search for an edge that takes us in a good direction, and we keep moving and moving around between corners until we find the best one. So to formalize that, we start at some vertex, we examine the neighboring vertices, we evaluate whether C transpose X is already optimal. If it is, we're done. If not, then one of our neighbors has a better C transpose X. And we move to the best neighboring vertex. So this is a greedy approach. And we iterate over these steps of re-examining the neighbors and going to the neighbor with the best cost. In a greedy way, we iterate over these until we're done. The specific steps correspond to some linear algebra calculations. And the problem of why it can be slow, the number of possible vertices, the number of corners of the polytope can be very large as a function of the cardinality of x, the length of x. It can be exponential in x. And sometimes we're lucky. And along this very large number of polytope corners, we quickly convert to a good one. And actually, that's often the case. That's why typically Dantzig's approach is reasonable. But sometimes there's a worst case where we need to go through a significant portion of these vertices. All right, so again, linear program, the big idea here is that number one, many problems can be approximated as linear in terms of what we're trying to optimize. And for these problems, we have a canonical form that many other problems can be converted to the canonical form. And the Dantzig and interior point method, they've been designed very well to handle the canonical form. And because of that, we can solve other types of problems that don't exactly fit the canonical form, but can be manipulated to fit into that form. So that's it for this linear programming material, and we'll continue next time.